In this lecture, we'll be talking about practical issues for 2D spiral RF pulses, and then we'll talk about how to design echoplanar pulses that are spatially selective in 2 dimensions. So as a refresher, in the last lecture we talked about 2D spiral RF pulse design. And we defined a few steps. So step 1 was to design the spiral k-space trajectory, k of t, where the resolution of this trajectory is equal to 1 over 2 times the maximum k-space value that is reached by the trajectory. And the field of view for an n-turn spiral is equal to 2 times n times delta r. So we can establish one of these parameters and get the other from it. Then you define a target transverse magnetization or MXY pattern and calculate its Fourier transform. That gives you the k-space weighting function w of k. Then we have to resample that w of k, that k-space weighting function, onto the trajectory that is defined by the spiral k of tau comma t, and that gives us the resampled k-space weighting function on the trajectory w of k of tau comma t. And finally, we scale that result by the speed with which we're moving through k-space, which is given by k prime, the time derivative, tau comma t, times the resampled k-space weighting function. Here, the b1 of tau is the sample of the k-space weighting function w of k at the location k of tau comma t along the trajectory, weighted by the instantaneous speed with which you're moving along the trajectory. So if you note that earlier we noted that taking the derivative of the k-space trajectory, which gives us the gradient waveforms, is really an estimate of the density compensation function. And the density compensation function magnitude of d of tau. This works okay for single-shot spirals, but it's no good for interleaf spirals. That doesn't mean we can't design interleaf spiral waveforms. You just have to come up with a different density compensation function. So here's an example of an RF pulse that produces the minimum resolution pattern that we can produce. That is the sharpest possible feature that we can produce with this given trajectory, k-space trajectory defined by the gradients gx and gy here. This is the RF envelope that we play out simultaneously with the gradients. This is the k-space weighting that is equal to b1 of t divided by the speed with which we're moving through k-space, gamma g of t. And here's the transverse magnetization pattern that we produce. In this case, the RF pulse is fully real, so the magnetization produced is fully in the y dimension. And so let's look at the side lobe geometry of this pulse. This is a 12-turn spiral pulse with a 4.5 millisecond duration, and where the trajectory is using a constant slew rate. That is, the derivatives of the gradients in time are constant. It reaches a 1 centimeter resolution, that is delta r is 1 centimeter, so Kmax then has to be plus or minus 0.5 cycles per centimeter. The space bandwidth product then comes out to be 4, and the shape of the RF pulse is a windowed jink RF. And what we get when we look at this in the spatial domain is that we get side lobes at plus or minus 24 centimeters, and then again at plus or minus 48 centimeters. That is multiples of the field of view of the spiral trajectory. So here's an example where here's a zoomed in view where we see the first side lobes, and then if we zoom out by a factor of 2 further, we see the second side lobe structure appear. Right? So we get this repeating side lobe structure. You can see that it goes out to 3 side lobes here as we keep moving out. And probably the most significant practical issue that we run into with spiral RF pulses, with getting a good spiral RF excitation, are gradient delays. So the definition of a gradient delay is the time lag that you have, the time lag between the RF and gradients. That is, it's the time lag between when a gradient waveform is requested and when something actually happens in the magnet bore. So the RF basically is always played out exactly when you want it. So we typically get a time lag between the requested and actual gradient waveforms, and this results in a time lag between the RF and gradients. So this then consequently manifests as a delay between the start of the RF pulse and the K-space trajectory. That is, there's a mismatch, right? We start playing the pulse too early compared to when we actually start traversing the trajectory. It can come from many sources. It can come from just digital delays in generating the waveforms. It can come from the frequency responses. Of the gradient coils and its amplifier, and their amplifiers, because they are RLC circuits. And it can come from eddy currents. These are currents induced in metallic structures in the bore. Typical delay numbers range between, on a whole body gradient system, between about 40 and 150 microseconds. Sounds pretty small, but it can be significant when you're looking at trying to get a good excitation. So let's look at it in a little more detail analytically on what a delay does to a constant angular rate spiral excitation. So here we're going to give an analytic expression for the spiral waveform, in that we have some Kmax we're going to reach. We start at 0 and we go out in time. This happens to be a spiral in waveform, right? Since at the beginning of time this quantity is going to be maximized, so we're going to be far out in K-space. We're going to start far out in K-space and then we're going to circle in. And then this is the phase angle in the KX KY plane. So we're going in circles, right? We're going linearly in circles towards the middle of K-space, right? Starting out and then scrolling in and in and in. And the RF pulse will be given as well. So then the K-space trajectory, K of t, accounting for a time delay delta, is given by K max times 1 minus t minus delta over capital T times e to the I 2 pi times n times 1 minus t minus delta divided by capital T, the duration of the waveform. And if delta is quite small, then we can separate it out. That is, we can neglect the term in the amplitude here, amplitude factor there, and say that this is approximately equal to K max times 1 minus little t over big T times e to the I 2 pi n times 1 minus little t over big T times e to the I 2 pi n delta over T. And then this guy here is the original expression that we had for the K-space trajectory. So now we just have this phase modulation on it. So that's equal to K of t times e to the I 2 pi times n times delta over capital T. Now recall here that K of t is defined as a complex number in the kxy plane, where the real part is kx of t and the imaginary part is ky of t. So that means, so what we've done here is we've applied a rotation, a phase rotation in this complex plane. And that means that we have, in multiplying by e to the I 2 pi n delta over t, this multiplication is a rotation of the trajectory by 2 pi times n times delta over t radians. And what happens when you rotate an image's Fourier transform? The image itself rotates. So if you crunch the numbers out here, let's say that you have this 12-turn spiral that we talked about earlier, and that it's 4.5 milliseconds long, and then you have a delay of 16 microseconds. That's around usually maybe 4 samples on a GE scanner at least. So then the angle, the phase angle you're going to get, or the rotation angle you're going to get, is 2 pi times 12 times 0.016, that's the delta, divided by 4.5 4.5 milliseconds, which is equal to 0.27 radians, or about 15 degrees. This is something you're really going to notice. And you're going to especially notice the rotation if you're exciting a pattern with any kind of asymmetry with respect to the center of the field of view. Since if you're exciting a circularly symmetric pattern with a spiral RF pulse in the middle of the field of view, you're not going to notice if it rotates. So here's an example showing the effect of gradient delays on a constant angular rate spiral. So this is the center of the field of view, and we have modulated the spiral RF pulse to put its center excitation here at a radius of 10 centimeters. So you can see that as we increase the delay from 4 to 8 and then 16 microseconds, that's what we solved for, we get a rotation of the excited pattern here. So overall, then the delay produces a rotation about isocenter. Here's a more practical case of a constant slew rate spiral. A constant angular rate spiral isn't particularly time efficient, but a constant slew rate spiral runs as fast as you can possibly drive the gradients. So this is what more representative of what we would see in practice. Here's with no delay, 4 microseconds, a slight rotation, but not much other distortion. But then you see, as compared to the constant angular rate spiral, that you start to also not only see this rotation, but also additional side lobes that pile up. So here, in this case, with practical constant slew rate spirals, we get both a rotation about isocenter and a distortion of the selected volume. And this happens because we're not moving through k-space with a constant angular rate. So different turns of the spiral are delayed by different amounts, and that causes incoherency between the consecutive turns of the spiral excitation. So the effect of the delay is primarily a rotation with little other distortion for a constant angular rate spiral. But for more practical gradient amplitude and slew rate optimized spirals that you would use in practice for the shortest possible excitations, you get a rotation that is dependent on the position of the k-space trajectory, of the k-space radius, and that gives you dispersion. And the result is that high and low spatial frequencies get out of alignment, and that results in distortions. The next practical issue for spiral RF pulses is off-resonance. There are lots of different possible sources of B0 variations. They can come from magnetic field inhomogeneities, tissue magnetic susceptibility variations, they can come from chemical shift, for example, between fat and water, and they can come from eddy currents. All of these cause variations that manifest as off-resonance. And they have the same overall effect on the excitation. So as in image reconstruction, the effect of off-resonance on spiral excitations is blurring. So let's see what happens here. The ideal k-space weighting function, W of k, is equal to B1 of t divided by the speed with which we move through the k-space, k prime of t. And if the RF is applied at an off-resonance frequency of omega, where omega is the sum of all the sources of the frequency shifts, the actual weighting that we get is B1 of t divided by k prime of t times e to the minus I omega t. So this is considering just like one spatial location with an off-resonance omega. Then for a spiral excitation pulse with a constant angular rate, we have k of t equals k max times 1 minus little t over big T times e to the I 2 pi n times 1 minus little t over big T. And its magnitude then is just k max times 1 minus little t over t. And then we can use this expression to write an expression for t as a function of k, right? We can rework this expression then into an expression for t as a function of the k-space absolute position in k-space, which is equal to t times 1 minus k magnitude k over k max. So you can guess what's going to happen next. It's that we're going to make this substitution for t up in this expression for the off-resonance modulated RF pulse, and that'll give us b1 of t divided by magnitude k prime of t times e to the minus I omega times capital T times 1 minus magnitude k of t divided by k max. And then this gives us the desired weighting, of course. The first term is equal to the desired weighting but then we also have a phase aberration that is k-space location dependent. E to the minus I omega t times 1 minus magnitude k of t divided by k max. So this is the phase aberration. And you note that this phase aberration depends on the k-space location. Okay? So it's not just a global phase shift. So here's a plot of the phase that we end up getting across our k-space as a function of absolute k-space location. Here's the argument of the complex exponential that we end up multiplying the k-space weighting by. You can see that it starts large and attenuates down to 0 as you get to the outskirts of k-space. And if we take that argument and then evaluate it in the complex exponential, this gives us our phase shift, which has imaginary part as the dashed curve here and real part as the continuous curve here. So this example is a relatively small aberration. For less than about space bandwidth over 4 cycles, we get just a blurring of the impulse response. For more than this, we start to get more blurring and also a significant loss of amplitude because you start having different parts of the k-space weighting cancel out with each other. So here's an example illustrating the effect of off-resonance. Here's an on-resonance excitation. Here's with a 220 hertz shift. This is like fat at 1.5 Tesla. You can see that it's blurred substantially. Here's 440 hertz, which is like fat at 3 Tesla. You can see that it's blurred and it's starting to be attenuated. And at a very extreme amplitude of 880 hertz, you get essentially completely lost. You've completely lost your excitation. Here, in this case, for this 4.5 millisecond pulse, the 220 hertz corresponds to 1 cycle of phase over the pulse length. Here are one-dimensional plots of the same thing. So you see that when we get up to 220 hertz, we've already lost some amplitude of the excitation. When we get to 440, we have 2 cycles of phase over the pulse length, and we have substantial loss of amplitude. And at 880, it's not really recognizable. So now we've covered spiral RF pulse design, and we'll move on to echoplanar spatial pulse design. Unlike spiral pulses, echoplanar pulses can excite patterns with non-isotropic spatial resolution. That is, the pulse designer is free to make the pattern sharper in one dimension compared to the other. You also get a side lobe in only one dimension, that's the phase-encoded dimension. So first, let's take a look at the different options that we have for echoplanar trajectories. That is, spatial echoplanar trajectories, as compared to echoplanar spectral spatial trajectories, which we'll talk about in a later lecture. So the first is the blipped EPI trajectory, which is rectilinear as a function of k-space. Right? It covers a Cartesian grid in k-space. It's the most efficient because it goes both left, right, and right, left in k-space, alternating for every other line. It's commonly used for spatial pulses, but because it is blipping, changing directions every other line of k-space, it can be sensitive to eddy currents and timing delays. So let's plot out what the gradients in the k-space would look like for this trajectory. So here are the gradients. It's bipolar, and on each plateau, we play some RF. So this here I'm illustrating is the GX gradient. And in between each plateau, we play trapezoid blips in the other channel. You know what I should do is use a different color for that. So in the Y channel, we play a gradient blip between each plateau of the X channel. So the blue blips there are GY. And this gives us a K-space sampling pattern that is rectilinear. We start going left to right, and then go right left, and alternate every other line. And we can define then the extent that we reach in each direction. We'll call this 2 times ky max, and we'll call this 2 times kx max. And you can appreciate here that ky max and kx max don't have to be the same. The other thing to note here is that in the y dimension, that is the blipped dimension, we take discrete steps in k-space. That is, we're going to see significant side lobes that we have. So we have to sample this finely enough. We have to bring the lines close enough such that our aliases are where we need them to be. So we're going to have aliases just like we do in echoplanar imaging. And then conversely, along the x-axis, we are doing frequency encoding, so we don't have aliases anywhere relevant. And we can consider it to be continuous sampling for the purposes of practical imaging. The other major option for echoplanar trajectories is flyback. It's also rectilinear, but it's less efficient because you always try to scan going the same direction. You always try to make all your your frequency encode, the trapezoids go the same direction. But it's almost completely immune to eddy currents and timing delays, which makes it very, very robust. You don't really have to compensate any of those effects. So a flyback trajectory looks like this. You move along, you play out flat plateaus in between which you completely rewind your position in k-space. So this is the gx gradient, and this is the gy gradient, which you play during the flyback portions. These big troughs here are called the flyback portions, where you completely rewind the phase that you've accrued in kx. Note that in the blipped EPI case, we play RF during the flat portions, so that's both the positive and negative portions of the trajectory. But for the flyback case, we only play RF out during the positive portions. And then the trajectory that we trace out kind of zigzags. So we zigzag up and down and play out RF during the parts where we're going straight across the KY axis. And here's an example of a blipped EPI set of gradient pulses in the k-space trajectory, which has the same parameters defined, right? We're playing both the positive and negative lobes of the gradients are the same, and we have blips in between each lobe. And that traces out a Cartesian grid in k-space, where we have potentially independent resolutions in ky and kx. Conversely, here's the flyback case, where we only play our RF out during the flat portions, the positive flat portions of the gradient trajectory, and we just try to zip back as fast as possible with the minimum time in between the flat portions. And then likewise, we play with gy gradient blips in between each positive portion. And this gives us a zigzag pattern in k-space, where the diagonal portions are the retraces that we use to get back to the same starting point every time we zag across and play RF. So in echoplanar excitations, side lobes will appear in the y dimension, or the phase-encoded dimension. Of course, you can rotate the trajectory as you wish, but here we're calling the y dimension the phase-encoded dimension. And so that is, in the image domain, we're going to get replicas of the excited pattern along the y-axis. So here's a replica here, here's a replica here, and this is the pattern that we actually wanted to excite. And the distance between these is given by L minus 1 times delta y, where delta y is the resolution that we reach with the trajectory. And that's given down here as 2 times ky max over L minus 1 inverse equals L minus 1 times delta y, where L is the number of lines that we scan with the trajectory. There's also a field of view over 2 side lobe that can appear in in conventional bipolar blipped echoplanar trajectories, and that's caused by eddy currents and timing delays in the blipped case. And we usually try to have to calibrate the pulse to suppress that. We're not going to go through the gradient design in detail here, but note that there are essentially 3 trapezoids that we have to design for an echoplanar pulse. We have to design, the first one is the flat pulse, the pulse, the gradient, the GX gradient pulse that during which we play the RF. Typically we only play RF during the flat top there of this trapezoid, and then we just repeat it L times to form up the entire GX gradient. And in between those, the second trapezoid we have to design is the blip that we use in GY. Note that the blip here is the same for a flyback or an echoplanar or a blipped trajectory. And then the third trapezoid we have to design is the refocusing lobe, which will have area of 1/2 times this trapezoid's area. Right? This trapezoid's area should be twice the area of this, such that this lobe brings us back to the center of K-space, such that we don't leave any large phase across the field of view with the RF pulse that might cause signal cancellation. To design 2D echoplanar RF pulses, there are 2 major options. There's a general approach, which is the same as spiral, but in this case, the rate with which we're going through K-space is a constant, for most EPI trajectories at least, when the RF is on, so we don't have to consider it. It makes it simple. There's also, the other option is to design a separable, is to use a separable product design, which is easier than the general 2-dimensional approach, but it's restricted to separable, that is rectangular, target patterns. So we're going to talk about this in a little more detail. So the separable product RF design, here in this case we assume that the K-space weighting we want is equal to some envelope, some weighting in the slow dimension, which is a function of ky, the slow or the blipped dimension, times a weighting in the fast dimension, which is a function of kx. So again here, as of ky is the weighting in the slow dimension, or the blipped dimension, and AF of kx is the weighting in the fast or frequency encoded direction. And so what we're going to do here is we're going to produce a weighting of AF of kx going this direction and multiply that by a weighting of AS in the other direction. So we're going to have to sample KS, the AS envelope, using the AF functions. So in other words, the RF is a sequence of AF sublobes, each of which is multiplied by samples of the AS of KY envelope depending on that sublobe's KY position. Sublobes you could also say subpulses, right? So the echoplanar pulse is made up of a series of subpulses, and each one is weighted, they're identical subpulses, and each one is weighted by its position in the AS of KY envelope. And here's an example of a product pulse design of a 15 millisecond echoplanar pulse, which is made up of these time bandwidth 4 pulses in the fast direction, right? You can see they only have one side lobe each in the fast direction. And then we have a higher time bandwidth product of 8 for the AS envelope of AS of KY envelope, this sharper pattern in the slow direction. Okay, so this is here you can appreciate how we're going to have different widths or sharpness in each direction. And so here's a depiction of a pulse that has the same time space bandwidth product in both directions, and we also achieve the same resolution in both directions. So that is, we get a time bandwidth pulse both for the AS envelope, right, with one side lobe on each side, and then also for the subpulses we also have one side lobe on either side of the main lobe. Here's the gradient trajectory that we play this out on. You can see that the RF is played out only during the flat parts of the gradients. And here's an illustration of the excited volume. So this middle excitation is the one we actually want. And then these guys on the periphery are the aliased excitations that occur at plus or minus 13 centimeters.